Hey guys, welcome to our third general body meeting. Today, we're just going to be going over a few things, a few project updates on everything that started, a few design opportunities for anybody in here if they want to go ahead and take on a small or individual or group project that'll help the team going forward. We're going to talk about office hours, and that's in quotes because it's not really office hours. I just kind of have a place where you can come talk to me. And then some presentations, just moving forward with each of these lesson, seminar type things. One on the basics of motors with propulsions, one giving a demonstration on Open Rocket, and the last one on recovery. So just to get started, just updates from our hybrid team. We're bringing 8 teams, which is pretty cool. Most of the other universities that are involved in this are bringing 2 or 3, so we should be able to dominate the field this year. There's 8 other schools competing, and that's just in Florida, so that's what's going on there. We had a meeting yesterday, and I was going to ask Kyle if he wanted to go over what that was really quick, but I don't think he's here. So was somebody from the hybrid meeting yesterday just want to talk briefly? Any progress made?
Yeah, so basically what we did is we split up our 8 teams. We assigned tasks to each of the team members, so like secretaries, the manufacturing leads, and the supply leads, and and we did just a general basic overview of what hybrid motors are and how you put one together. We were going to do a demonstration, but we couldn't find any degrees. So that's kind of where we left it. I don't know when the next meeting is, but that'll be next week.
Cool, thank you very much. On the propulsions research side of everything, last Thursday we had a sugar motor event. And so thank you all to everybody who came out. We actually built our own motor and did a static test there. And in the picture, that's actually looking down the tube that we've got, seeing the results after we burned it. So that's pretty neat. And we built 2 other spare grains. So we may have a potential launch next weekend, actually trying to launch one of those motors. We don't have the details for that figured out right now. As soon as we do, I'll let you all know, send out an email, figure out how we can do transportation, because it's probably going to be like a 2-hour drive to our launch site. That's what's going on there. We actually have a video of the static motor test. I'm going to bring this over first really quick. This should be what went on late Thursday night. So that's what we built with just sugar and potassium nitrate. Yeah, okay. And so that's pretty cool. Let me jump back to the PowerPoint really quick. There we go. So that's what's going on with those 2 groups. And with that, I want to jump into some of the projects, the individual group things that I want to start working on. In that video I just showed you, there was a test stand that we used. It was actually this test stand turned upside down. And that's what we use to test our rockets. We test them before we actually apply them just the motors to make sure that we can get accurate data about what the thrust is going to look like, the flight profile, and all of that. We need a new way to work with the one we've got or to design a new one. So the one we have right now, I'm not sure if you can tell, there's a PVC pipe in there. And that only allows for one very specific motor diameter, which isn't really that useful to us if we want to try something else. And you can also see that it's clamped together with a big cinder block on the top, which is not the most secure way to have a rocket. So what I'm looking for is somebody to go ahead and if they want to modify this one, go ahead and mock this up on SolidWorks, do an analysis on there with those specs I have in there, just the 3,000 newtons of force, because that's kind of what we're looking at in terms of our launch this year, and see if this is first capable of holding that load, because we're not sure. And if you're designing something totally new, just be able to measure the force over time, have it clamped into the ground securely instead of putting a cinder block on top, and have a stand that's fit for a variable diameter motor. And with that, this actually has a load cell in there right now, which is how we measure just the thrust on the rocket. And the only person who has a code to interpret that is Jimmy. So the next project that I want to bring up is actually designing some way to acquire data from that load cell. So this is a project more fit for somebody who has a little bit of experience working with LabVIEW or like the data acquisition software. So if you've taken MomLab or you're taking it right now, this is something kind of geared towards you. We want to be able to actually interpret the data that we get. So get our impulse, our average thrust, our max thrust, our thrust curve, and our burn time. Over there on the right, you can actually see a thrust curve from a manufacturer. Typically, the manufacturer thrust curves are pretty good, but we always want to test our own motors to verify because each different batch that they make has a little bit different characteristics. So that's why we're doing a lot of this. Stepping away from the static motor tests, the last project, the last group or individual project that I want to work on is a fin mount apparatus. So typically, our team has a lot of problems mounting fins just because it's a little bit, it's difficult to get them in perfectly perpendicular. I have a pretty poor isometric drawing of just one fin sticking into a rocket here, and this is looking at the rocket edge on, or from the back. And our problem is that, so this is the fin that we have normally sticking out, and ideally it's straight out. But because we can't get inside, we have no way to measure exactly how perpendicular we are to the surface, a lot of times we'll have our fins drift from side to side within these dotted lines, if you can see those. So we're looking for a way, if you can design some sort of apparatus that might clamp around the outside, hold the fins in place, and have it set up so that they're all perfectly perpendicular from that tangent plane to the side. If you can work on designing that, that would be awesome. So with all these projects, with the exception of the LabVIEW software, the most you'll really need is a bit of creativity and then working in SolidWorks to try and actually model these. If you don't have any experience with SolidWorks, that's okay. This is an awesome opportunity to learn how to work with that. So we're looking for anybody to do that. If you're interested in these projects, come talk to me right after the meeting, and I'll let you know, put your name down, and start talking to you, and see what you're doing. Feel free to work with friends or whatever. This is just some stuff we need. Beyond that, I'm going to have office hours. I put it in quotes, again, because it's not really my office. It's just a room that we have available to us. And I'll be working in there at these times every week. So if you ever want to come talk to me about the rocket team or hang out and work and keep me company because I'll be living in there, that's fine too. A lot of times during this time I'm going to try and devote it to rocket team, but I'll do homework too, so it's like office hours. I'll just be there. The room does have a code to enter it, so you can't just get in there on your own. If I'm not going to be there, I'll let you know. That's what's going on there. And with this, I think I'm going to hand it off to Crystal to talk about the basics of rocket motors.
All right. Hello, everyone. My name is Crystal, who haven't met me before. I'm the propulsion research lead, and I'm going to talk to you about basics of rockets. So basically, rockets work on Newton's law of motion, where a reaction is equal to opposite reaction. The rocket is basically conserves mass and conserves momentum. So when you burn the matter inside the motor, the gases and the matter burns into a gas, and the gases create a pressure chamber. And there's going to be a pressure difference between the pressure chamber and the atmospheric pressure. And that's going to drive the mass outside of the opening, which is a nozzle. And I have an example here. This is actually mine. So I'm going to pass this around so you guys can see it. But here, there's a nozzle. And basically that's where Basically, liquids, they're kind of complicated because you're going to have your fuel and then you have your oxidizer. And you have to get the mass ratios correct in order for it to react perfectly. There's three types of liquids. There's your cryogenics, which you have to do by cold temperatures. Your hypergolics, which are like hydrogen peroxide is a hypergolic, and your petroleum, which is oil. Moving on, you have your solids, which is the left, and I'll talk more about solids later. And then on the bottom, you have your hybrids, which are usually solid, gas, or solid and liquid, and you can control the thrust that it produces. And then, okay, solids. So, for solids, you have your nozzle, and then you have your propellant. Your propellant is usually structured into grains, and those grains, based on the sizes and where your hole is, will give you different thrust profiles. After it runs through the grain, you're going to have a delay, and that delay is for right when your propellant ends, you're going at your max velocity. So you don't want your ejection charge, which throws out your parachute, to eject right when you're going at your max velocity. So you're going to have a delay where it coasts, and then once it reaches altitude, it's going to run out, and then the ejection charge is going to blow, and your parachute will come out. And that's basically the basics of solids. And here are a few baked grains that you can do. For those of you that attended on Thursday, I think we did something like a number, which, mouse. Well, it's the whole with the up, yeah. So different base grains give you different thrust profiles, as you can see on the left. And okay, rockets. So there's two different types of rockets. You have your model rockets, and then you have your high-powered rockets. Model rockets, basically anyone can use. They use A to G motors, class 1, and usually the rocket's made out of paper, wood, or plastics. For high-powered rocketry, it's class 2, so you need certifications in order to launch anywhere. Usually the motors are more than 160 milliseconds of total impulse, or more than 80 minutes of having thrust. Any hybrid motor is a high-powered rocket. If the rocket weighs more than 1,500 grams, it's also a high-powered motor, and if it includes any metal on the airframe. For certification for high-powered rocketry, level 1 uses an H or an I motor, and basically the alphabet dictates like what your total impulse is. So an H motor, the maximum impulse it has is 320 milliseconds, and an I motor has 640. So for every letter that you go down in the alphabet, you get double the maximum impulse. So for a J motor, it will be 2 times 640, which is 48, and so on and so forth. And then level 2 is JKL, and then level 3 is MNO. Beyond O is class 3, and that is not considered a high-power rocket. It's usually like an experimental to a J motor, and the motor that's going around is an I motor. This one is much bigger, so this is a level 2.
Alright, how's everyone doing? I'm John. I'm the propulsion dynamics lead, and I will be showing you guys make this work. How to use OpenRocket. So OpenRocket is OpenRocket is an open source rocketry simulation program that you can download for free off the internet. Search on Google, and you guys will find the website for it. Alright, so this is what the interface looks like when it comes up, right? So basically the reason I'm going to be going through this with you guys today is this is how you would, we're going to be modeling the full rocket on here too, but this is where you would start for say like a level 1 certification. So if a lot of you guys want to build the newer rockets or the newer rockets we have going on this semester, or if you want to do a hobby rocket by yourself, we'll definitely help you out with that. And this is a great platform to start with. So we'll start off basically, I guess from scratch. We'll start with a nose cone, so you guys can see. Alright, so we'll start with the nose cone. So basically, just to add a component, we start over here, and we wait for the. Okay, so we have a nose cone, and we'll go ahead and click on it to define some properties, and okay, I can't see this. And this is the kind of window that's going to come up, right? So, a couple things we want to look for. One of the main features we're going to be using is, well, first off, you're going to define the length and the base diameter, all that good stuff. I'm going to rush through this part because it's not really pretty self-explanatory. But this is the biggest one. So, a big problem with OpenRocket is that the density calculations that they do are not always accurate. So, a lot of times we'll take our own measurements for the mass or density and go ahead and override basically what OpenRocket says it is. So we would override the mass here and just enter in a, let's see, enter in a value. And go ahead and X out here. Alright, cool. So now that we have our nose cone, we get into the fun stuff. So we'll go ahead and do a body tube. Okay? And we come up with this here. You can rename it outer diameter, inner diameter. So I'm going to go ahead and walk you guys through basically how we did our level 1 certification rockets, right? So we'll do a 3-inch outer diameter with an inner diameter of about 2.875. Okay. So, and now we would go ahead and do an override here for a mass, and say we just want it to be about 14 ounces. I'm in pounds. Don't want it to be 14.1 pounds. Okay.
You're in pounds for this time too.
Oh, cool. Well, we're gonna have a really heavy rocket. Okay. All right. So this is also an important part of this that I'll come back to is right about here. So actually, we're not going to use that for that much. All right. And a big part of the rocket. Oh, I'm sorry. We need to do the link. Is we're going to have an inner tube where our motor is actually going to go. So we have now have our body tube with a 36-inch body tube. And the next step that we want, if you guys have seen any of the rockets that we've been passing around at different meetings, is we're going to want an inner tube to go in the back side of the rocket. And that's when our motor is going to go. So that's basically kind of like a motor mount for us, right? So we'll come over here to inner tube. And again, we want okay. That's not right. All right. So we're going to give our body tube, our inner tube, a specific outer and inner diameter to give it the thickness, and we'll go ahead and put that in the rear of the rocket. I'm going to stop going through like the entire calculations with you guys because this is something you can mess around with. But basically, you see that you can edit the outer diameter, inner diameter, the length, mass properties, things like that. And then the next step that we want to go ahead and do is throw fins on the rocket, right? So we come up here, we can set up different types of fins. We're going to do trapezoid fins, trapezoidal fins. You guys can mess around and do all sorts of different cool stuff if you want, and see what the simulations say. Basically, what we're going to have here is you get to specify your number of fins around the back of the rocket, pretty self-explanatory. Fin rotation and fin cant. So fin rotation would be basically if you're at an angle with the body tube, and fin cant is whether or not you're completely straight with the rocket body tube or twisted a little bit. Is that backwards? Yeah. So, and then the root chord is going to be basically the base length of your fin. So how far it's going to be on the actual body tube. Your tip chord is the top of the fin. So we have a fin, something like this, right? So this would be our base chord here, and this would be our tip chord. Okay, our root chord and our tip chord. The height, of course, is pretty self-explanatory right here. And the sweep length and sweep angle is just going to automatically recalculate for you, but it's going to be this sweep length here and then this angle, right? And then we could either do an override for mass characteristics or go ahead and something like that. We can go ahead and put in for component material. We can come over here and select what we would use. So a lot of times we'll use just wood. It's easily available and pretty cheap. But sometimes we'll use this stuff called G10, which is like a fiberglass. And so, a couple different characteristics you can mess with here that we don't usually use, but it's cool. It's a cool way to do things. And then the next step is, so when we launch the rocket, we want to be able to recover it. So we need to put in a parachute, right? So you can actually model a parachute here that's going to be used mostly in the flight simulations later on, which I'll get to. So same way we do the parachute, we'll just come over to select the body tube here, and then come up and select it would be a mass object, so parachute. Here you can specify the diameter of your parachute. In this case, for a level 1 rocket, I don't know if you guys came to the meeting, or I guess that'll be covered in a minute. For level 1 rocketry, we're only going to do a single deployment, which means basically we're going to launch it, and at apogee we're going to deploy a parachute. So you can actually tell OpenRocket this, and basically make your parachute in here, and then over here where it says deploys at, you're going to say you can select basically whatever you want, wherever you think it's going to deploy. But for this, first ejection charge is where we want for a single stage level 1 rocket, because the motor is going to burn through and then have an ejection charge on the tail side, right? So it's going to blow an ejection charge, and that's where our parachute is going to come. You can't say, if you said like at apogee, that would assume that you have an altimeter on your rocket, which is going to be able to tell your altitude and tell when it peaks over and then starts coming back down. So that's more so for if you're designing like an L2 rocket, level 2. And again, we just have the override for mass characteristics. You can specify your number of shroud lines depending on what parachute you have. Okay. Shock cord is another big thing that's actually going to be tied into your from your parachute into your rocket. Okay. And that's going to be another mass object here. So we come back to body tube and select the shock cord, and we would actually incorporate that into the design, right? So next thing is center rings. You can do all sorts of cool stuff like this this tube obviously isn't going to be like floating in space, so you need some centering rings. So you use centering rings to put around the motor tube, and then you can also use coupler tubes between two different body tubes. So if you want to do like a level 2 rocket, a lot of times you'll have to get in there for a payload or for an altimeter bay. So that's what you would use there. Wish I had some of mine to show you guys, but and the other really big part of open rocket is if we go to inner tube and we click on motor. Like I said, this is going to be our motor mount. So if we say this component is the motor mount here, then we can edit different configurations. We can say more than one. We can come down here and select motor, right? So this ties back into what Crystal was saying about propulsion. And basically, we're going to be okay. So this is what's going to come up. These are all of the different motors from different manufacturers that you can get pretty much, right? So if we go ahead and specify by designation, we can see the same classes. Okay, there we go. That's not going to work. Because I didn't specify the right diameter. But basically, these are all your designations here. We can see we start getting to B, C, E, F level motors, and then down to like the H and I that are required for level 1 or level 2 certification flight, right? So if we click on one of these motors, we can see. So say we want to come up and do H170, right? So it brings up a thrust curve for us, and it brings up some really important stuff that we're going to look at for choosing a motor for our rocket. This is something you're just going to end up playing around with a little bit. You can do the calculations if you like, but basically you have to find a motor that's going to fit exactly what your needs are, right? So this goes back to what Crystal was saying. We have our total impulse that this motor provides, and then another important one is burn time, right? So do you have your rocket on you?
Yeah, I'd like.
You want to pull it up so I can show? So basically, you have burn time is a really important factor because you may have the right impulse that you want with a certain motor to get up to the certain altitude you want. But if you say your burn time is, if that's the right impulse you want, but it's about an 8-second burn time, you figure that motor, you saw the sugar motor, that was probably less than a second. That was probably, what, maybe half a second. And you picture an 8-second burn time, that thing's going to get up there pretty dang high, and you're not going to be able to control the altitude. You're going to deploy a parachute, and then it's like bye-bye rocket, so you're never going to see it again. So you always want to be very careful when you're selecting motors, and that's just something you're going to play around with. We're looking for something like a very consistent thrust curve, so we don't want something that's going to be jumping up and down. I don't know if you've seen the videos from our L1 flights, but it wasn't fun. The motor didn't have a very consistent thrust. So it ended up kicking our rocket sideways, shooting it off into the distance this way, and then deploying a parachute and having the wind bring it all the way back to nowhere land, right? But anyways,
I have no idea what rocket this is, but it looks like it's okay.
That's pretty good. So we see that we have our nose cone here. You can look up at the components up top.